Hey everyone, I just want to do this quick video to talk about calibration techniques and just a sort of introductory little video about this. So first I want to pop over to our Canvas page. And if we are looking at our Chem 18L Canvas page, it looks something like this. All right, here we go. That's not it. There we go. So it looks something like this. And I want to point out a couple things. First off, the textbook. If you go to the textbook link, it should pop up like this. It should pop up like this. And our calibration curves discussion would be right down here. So right here is where we're looking at. You can click this link over here. Right here is a document that I want to look at right now together. So when you click that, it should pop up as this, and this explains different ways to do calibration, which calibration, we're just determining the relationship and numeric relationship between an instrument's response, which would be originally some kind of electrical signal that would be recorded in computer as a number. So between an instrument's response and the concentration of the analyte that we had introduced into that instrument, so that we can then analyze an unknown and get an instrument response and correlate that to a concentration of our analyte. So I want to start out when we're looking at this. The model I want to do today is I want to completely skip the linear regression. So in some previous class, you will have done linear regressions, and there's times when that's appropriate. For our purposes, the standard linear regression that you've been taught to use is really a bad model. There is a way to alter this to make it perfect for us, but let's skip that for now. And I want to go to really what's I think is the simplest decent model to apply, which is an average of response factors. So we're applying this to gas chromatography, mass spectrometry. So this is usually done with an internal standard. So we're going to walk through how to apply these steps to a set of data that was generated from this class. So I pulled up a student's data from a little while back, and I'll walk through the process of how to do it. And honestly, I picked it really quickly at random, so I don't even know if it's a passing calibration curve. We're just going to look through. It's from week 3 of the semester, the third calibration curve that the student had done. So hopefully it was done pretty well. And we'll go through the process of doing an average response factors curve with it. All right, so here it is. Oops, I did not do that well. Let's try again. Oops, that's not it either. There we go. Okay, so this is the information that I have so far, and hopefully you can see this on the screen. I'll move this over and size this. Okay, this should work. So if you look down here, it's probably hard to see on my screen, but you could pull the document open on your own later. It says first, calculate the response ratio of the target compound to internal standard. So that's what we're looking at here when we look at this data. Make it a little larger for the screen right now. But right now we have 6 standards, and they aren't the exact same concentration that we're using, but same process. And each of those standards were made to a known concentration: 10 parts per million, 25 parts per million, 50 parts per million, 100 parts per million, 250 parts per million, 1,000 parts per million caffeine. So when they were analyzed, they went through the gas chromatograph into the mass spectrometer detector, and these were the area counts for each of the analytes. So for caffeine, the first one had an area count of 405. That's the area gas chromatography data gives this constant readout from the instrument, increasing when caffeine is present and then dipping back down when caffeine is not present or when no compound is sensed. So we calculate the area underneath that curve where it went up and came back down. And so that was 405 for the first standard, then 991, then 4,000, etc., all the way up to 535,523. In addition, an internal standard at the exact same concentration, naphthalene, was added to all of those standards, and it read 186,000, 181,000, 202,000, 194,000, etc. We expect a little bit of variability here, but to be generally in the same ballpark. We expect the variability because that's its purpose in this analysis, is to account for variability in the injection process on the instruments so that we get a more stable analysis overall. So this is our data. We have standard 1 at 10 part per million with this area of caffeine, this area of naphthalene. Standard 2 at this known concentration with this area of caffeine, this area of naphthalene. So our instructions say, first, calculate the response ratio of the target compound to the internal standard. So we're going to say, so this is the ratio of the caffeine to the naphthalene. So we do equals caffeine area divided by naphthalene area, enter. And a neat little trick in Excel is if you want that same formula all the way down, is just click that button and drag it all the way down. And in each case, it will calculate the response ratio between the caffeine area and the naphthalene area all the way down. That's what we now call our response ratios. So instead of referring to either of these responses from here on out, we're going to just use this response ratio. Next, we go back up to the general instructions, except instead of using the caffeine's area, from here on out, we use this ratio number. So we calculate what's called an average or a response factor next. So for the response factor, we take the analyte response divided by the concentration. So this is what we're using for the analyte response from now on. So for the response factor, we take the analyte response divided by the concentration. And we can go ahead and drag that all the way down. So this is essentially the slope. If you think about what you learned about slopes, it's rise over run, right? So if you're thinking about this being a graph, this response factor, the analyte, it's like putting that on the y-axis, or sorry, the response putting on the y-axis and the analyte concentration on the x-axis. And it gives you these response factors, which is the slope of the curve, but they're all a little bit different, right? 0.000218, 0.000219, 0.00041, and then they get significantly different. These two are pretty far off, and then this is close to 0.002, and then this one is close to 0.002. So they should all be identical or pretty dang close to identical across the board. If any of them are not, then that might mean that there's some kind of a serious issue going on with the data. Oh, wait. And I think there is. I think glancing at it right now, this is not going to be a passing calibration curve. So I think I can spot it right now. There was an instrument issue here where the inlet liner got fouled, because I see this kind of thing happen from time to time when that instrument problem happens. But the way you'd proceed is the next step is you say you calculate the average of the response factors. So you calculate the average this way. You say equals average of all of this information. And that gives you the average slope of the line, the average ratio between instrument response and concentration of caffeine. Then, so that gives us essentially the slope of that line. Then you need to calculate a quality measure. If you're used to using a linear regression, you're just telling it to give you the R squared value, which is supposed to be close to 1. But here we can't do that. So we calculate the relative standard deviation of these response factors. So that's the percent RSD. And a relative standard deviation is the difference or sorry, the standard deviation divided by the average. So you would calculate equals STDEV is the standard deviation formula in Excel. Standard deviation of this set divided by the average, which you can retype that in, or you could, in theory, I mean, you could easily just click back on the average cell. And then we put that in percent form. So generally your passing criteria is something like 10% or 20% RSD, and this is way out. There's just a really unacceptable relative standard deviation, meaning we have a really serious problem. And let me actually walk through and make sure I follow the instructions for response factor. We calculated the average of the above response factors. We're evaluating quality by calculating a relative standard deviation. If the relative standard deviation is acceptable, which it is not, we can use the average response factor to calculate the concentrations of each sample, or quality control standard, where it tells us how to do that. So I'm going to pause right here and show you what this looks like and show you the issue of why this is so bad graphically. But the stuff that I'm doing right now does not have to be repeated. You don't have to do exactly what I'm doing right now. Then we'll get back to showing you how you would calculate the concentration of an unknown using this average response factor. So I'm going to go ahead and graph this information right here. And to do that, I'll graph the two things that we graphed earlier and make sure they're on the correct axes. So I'll insert an XY scatter plot. And remember, when we calculated the response factor, we put the caffeine to naphthalene ratio, column F. We did that on top. So that's what we want to be our y-axis. And then on the bottom, we want the known concentration to be our x-axis. So the easy way to check that, just glancing on that, is you look at your x-axis and see that it goes out to 1,000, as the top number is 1,000. And the top number here is 1,000. So that doesn't mean the known concentrations are on the x-axis. We can go ahead and add those labels if we want. You can generally go to like a chart design and just pick a quick layout that includes some axis labels if you'd like, something like this. And we can type in that this is concentration in parts per million. And this axis is our response factors. Or sorry, the caffeine to naphthalene ratio. And then each data point is essentially our response factor because it's concentration, caffeine to naphthalene ratio plotted versus concentration. And you can kind of see that they don't fit a straight line at all. They fit sort of a quadratic regression. They look sort of like a parabola that starts out flat and goes up. And you can plot a line showing with this slope, with this response factor slope, very simply. You sort of start at 10 and go up to 1,000. And you calculate what that would be. Now, keep in mind, this response factor is the response divided by the concentration. So if we just take this multiplied by the response factor multiplied by the concentration, that should cancel out the concentration and we just get a response back. So it's like if we took concentration of 10 and multiplied by that, the response factor was response over concentration, then our concentrations would cancel and we'd get just a response back. So you just say equals this times this. And we could plot this information on the same curve. So we can say select data, add another series, make sure our X values are concentration values and our Y values are the response values. Say okay, and for series 2, we'll just say okay. We can format that data series to, instead of making it dots, make a solid line go between those two data points, and we can make it a different color just so that it's easier to see. And you can see that slope of the average RF is down here. It doesn't follow the line at all. This line curves. It's not a linear type curve. This is the trend line that would be created by using that average RF. So you can see it's bad data, and that's what this RSD showed us, that this trend line, that average slope of this line will definitely not match this data. So anyway, that's the pause. That's how you see what it looks like. That's how you can check what the line would look like with using this model, the average response factors model. Let's go back to say, how would we calculate a concentration, assuming this was a good curve? What would we have done? So what would we have done, assuming this was a good curve, is you would then analyze an unknown. And now we don't have a known concentration because that's the whole point. It's an unknown. We would have a caffeine area, and we can just make something up here. Let's make it 200,254, and a naphthalene area. So the first thing you would do is, just like up here, you would calculate the ratio of the caffeine to the naphthalene. And then you would want to calculate the concentration. And the idea here is the same. This average RF, this average response factor, remember, the response factor was calculated as the instrument response divided by the concentration. So if now we have an instrument response here, this here is our response, then the way that you get the concentration, the calculated concentration, is you divide this by the response factor, because that cancels the responses and gives you back a concentration. So we want to go into this cell over here and say equals this response divided by the response factor. And that lets us calculate that based on this response of caffeine to naphthalene, that would be calculated as 995 parts per million. And we would generally trim this. Go ahead and round this down. You don't want it displaying all those numbers. 996 parts per million. And now that's your calculated concentration in parts per million. Okay, so that's actually it. Hopefully that makes some sense, and you can try to replicate that with your own data. It is possible. Well, well, let me actually get to one more thing. So not going to hang up quite yet. So if you go back to our Canvas page, and you go to the course documents, class documents. So I will be handing this out on Friday, but I'll give you a little hint here. So if you want to see if your calibration curve is successful, hopefully this displays better for you. If you want to see if your calibration curve is successful, the average response factors usually needs to be less than 10%, except a big caveat is that in your standard operating procedure, it may allow wider limits than that. So you should go look in your standard operating procedure, see what your specific control limits are for a successful calibration curve. And in that student's data, I looking at the data, I know exactly what's happening. I will occasionally approve use of a quadratic regression instead. So if yours fails, it's not necessarily the end of the story. We'll look and see why it failed. If it's clearly a quadratic shape, if everybody's in the class is a quadratic shape, then we know it's the instrument's fault and not your fault. And we can consider switching to possibly using a different calibration model. That comes with some caveats. There's some debate about whether this is appropriate to use or not. And we can talk about that a little bit more in class in general, but that's why you need approval, because it's sort of fraught with some arguments about whether that's a good model or not. So in any case, that is the end of this discussion. Hopefully you can replicate that with your data, and we can talk about it on Friday.